Hello, everyone. Thank you, Linus, first for this introduction, and thank you also for inviting me to talk here today. And as Linus has mentioned, I would like to tell you a bit about this Python package that we are developing at the University of Stuttgart, which is called BayesValidRox, and it focuses mainly on surrogate-assisted Bayesian validation of computational models. So for a bit of a background, I am part of a collaborative research center. In German, we call these SFBs. And the specific CRC focuses on porous media and modeling different processes in porous media. The CRC is divided into different subgroups, where I personally am working towards the development and realization of uncertainty-aware validation benchmarks. Today, I've brought you a small example here, so you get a better feeling of what this actually means and what kind of problems we are tackling there. And this is biomineralization, specifically calcium carbonate precipitation. And this is currently very interesting for stabilization of soils and also for things like self-healing concrete, so to close fractures in materials. And we were focusing on the enzymatically induced calcium carbonate precipitation. I will just shorten this to EICP. This consists of these two reactions you see here, and there's other processes that are associated with it, such as the dissolution of already precipitated calcium carbonate, as well as different transformations between forms of calcium carbonate. We have some experimental results from some colleagues of mine. So these are images that were taken from a microfluidic cell. So just imagine it's like a very small cell with solid columns. These are the large black dots you can see here. And they performed EICP in the cell over a span of 4 hours, having flow from left to the right. And you can see that the images become darker over the time. And this is the precipitated calcium carbonate that you see here. And you can also see that this precipitation doesn't happen uniform over the whole spatial domain, but there's areas where there's more precipitation and where there's less precipitation. Here, I would just like to highlight this flow path at the top where there's almost no precipitation happening, so the flow can go through unhindered. To get a better understanding of the processes that lead to these results, specifically to the flow paths, we built a computational model. And this model has been implemented in Dumux, which is a free and open source simulator and a research code that is written in C++, and it's also being developed at the University of Stuttgart. And it focuses mainly on just exactly what our CRC does, so flow and transport in porous media. And you can see here that we have managed to create these similar linear features as in the experiments, but there's some results where we have them and some results where we don't have them. And also we tend to have multiple flow paths and not just a single one. So we wanted to compare the data to the model to get a better understanding of which processes are important here and which actually would lead to this result. So yeah, general task is compare this model against the data. But of course, there's also cases where we have to compare models against each other. And well, we are here to also talk about uncertainty quantification. There's uncertainty on both sides of this equation. We have uncertainty in the model because we don't fully understand the processes, but we also have uncertainty just from uncertain parameters, which lead to different results. And we have measurement uncertainty for the experimental data. In addition, we are looking at a case here where the computational cost for the model is rather high. So the specific Dumux model takes about 8 hours to run through for each single model run. So I cannot just let it run for, I don't know, a lot of times to do some accurate comparison to the data. And also there is a lack of experimental data for these porous media cases because there's just not really many experiments being done, and there is not many repetitions of the experiments as well. So to help combat this lack of data, we use surrogate models. These, of course, mainly help with the lack of computational data, so model runs. And then we also use a Bayesian approach here to help us to consider the uncertainty when comparing the models to the experimental data. So in total, we're looking for something that is easy to use and that allows us to combine these surrogates with Bayesian evaluation and comparing different models against each other and against this data. And this is where we then decided to create our own package. It's a Python package. It's open source, so you can easily use it. And today I want to just give you a bit of an introduction to how this works by describing the typical workflow and also giving you some code examples. These are code snippets that were taken from the project for the biomineralization. We start out by just making sure we can run the model. Here we currently have an interface that uses PyLink, but of course we want to extend this to use UMBridge. I will talk a bit more about this later. And when we are able to run this model, we also need to set our experimental design. So this includes setting all the prior distributions for the uncertain parameters, and also in this case, deciding on different sampling methods for the samples that our surrogate model or our meta model will use to train on. The code for this, you can see here. So this first block is the definition of the priors for the uncertain parameters. There's 4 uncertain parameters in this case, and the priors I just set from some discrete samples that I have. I could also set here, for example, that the prior type or the marginal type should be, I don't know, a normal distribution with some characteristic values. But I chose here to just use the discrete samples. And on the right, you can see how the distributions look like. The bottom part of the code describes the definition of the experimental design. And I did not choose actually one of the sampling methods I just talked about, but I said I wanted to use some samples that I had run my model on previously. So these are just being set here. And you can see these samples as red dots in the distributions. Now that I have done this, I can start to think about my surrogate. And we typically use polynomial chaos expansions in BayesValidRox, mainly what we call the arbitrary polynomial chaos expansion. This is a type of PCE that does not need you to choose a specific type of polynomial to build your expansion on, but it just uses the prior distributions that you feed in to your experimental design and uses these to create your PCE. There's different properties that you can set here, different truncation schemes, regression types, and you can also add sparsity to your expansion, which helps to further reduce the number of data points or number of model runs that you need to get a good approximation for higher degrees. There's also GPEs available in BayesValidRox, but also for the other results I show you today in this presentation, the PCE was used. And there's dimensionality reduction by a PCA. The normal surrogate, as it is described here, will just train on the data you feed it or train based on the samples that are defined in your experimental design. But you can add sequential training or active learning by using what we call the meta model engine. So it's what makes a sequential design run. And there's different options here for exploration and exploitation. For the example, I did not choose to use a sequential design just based on the high computational cost associated with my models. But you can see here, I set my meta model to be an APC, and I chose this FastAAD as a regression method, which is one of the sparsity-inducing regression methods that are available in BayesValidRox. And then I set my range of polynomial degrees, and this last one is my truncation scheme. My meta model is trained with this one single command, and this will return to me a trained meta model that I can just evaluate. And here on the bottom of the slide, you can see some of the evaluations. And these, as we wanted, they contain these linear features that our model also has, and also that we want to be able to compare it to our data. In addition, I can just look at some other statistics. I can just ask my PCE for the mean and for the standard deviation of my surrogate, for some training diagnostics, and there's also methods for regression accuracy and sensitivity analysis, specifically total Sobel indices here, because these are really cheap to evaluate and cheap to compute for APCs. Now, so far, all that we've done has been excluding the data that we have. But we can use this in when we do inference, so when we try to estimate the parameter values that give us our data. And here there is the class that also allows you to set the uncertainty of the data and choose between MCMC and rejection sampling. And here there's just two small images of what these results look like. So the left one is your posterior, and the right one is something else that you get, which is the plots of your BME of your surrogate or of your model given by your surrogate, as well as comparing it to the TOM BME. And the code for this is quite a bit longer, but that's just because of all the options I said here. This first paragraph is the uncertainty of the data is set here to be Gaussian with a specific standard deviation based on the actual values that are in my data. And then I set lots of bootstrapping options for the inference, some MCMC parameters, and let it run. Okay, the next thing that BayesValidRox can do is allow you to compare models against each other given some data that you have. There's three options here. The first is simply to use a Bayes vector to compare pairs of models given some data. And then there's different types of interpretation based on how important or how much evidence your result could give you. And the second type is to use Bayesian model selection, which is usable or applicable for a set of models, not just two. And this will assign a weight for each model in your set of models. And the last is what is called a model justifiability analysis, which not only compares the models given the data, but also given other models. So it kind of lets other models run and uses those model results as data to compare the models against each other. Now, sadly, there were no real different models that I could compare for this biomineralization example. But yesterday I managed to get it to run that BayesValidRox accepts a UM-bridge model. It was actually much faster to implement than I expected. It's exactly this much. So this is all the code that you need to use BayesValidRox with the UM-bridge model just as it is right now. Here it's just for the tsunami model that was in the tutorial yesterday. And I created two models and two surrogates for level 0 of this tsunami model and level 1. I did not do level 2. I thought it would probably take too long to have it ready today. And this is then how the model comparison should be set up. I just define my models, set some bootstrap options, and let it run. And here are some results. So these are results from comparing these two tsunami models against data that I also pulled from one of the tsunami models. It's the model with level 0. And it might be a bit small on your side, so I will just tell you the Bayes vector and the Bayesian model selection, they both accurately find that the model M0, so with level 0, is the one that matches better to this data, which is great because that's also what actually is true. Interestingly enough, for the model justifiability analysis, model M1, so level 1, was chosen to be much more interesting and much better than model M0 in all cases. So I did not expect that, but maybe that's something that was expected based on what the models actually do on the inside and the differences. So we have now looked at a lot of options that are available in BayesValidRox, and I would just like to briefly summarize them before we come to any conclusions to finalize this presentation. Firstly, in BayesValidRox, you have available easily set up surrogates with a variety of options that include intuitive definitions of the price and the uncertainty of your data. And of course, there's Bayesian methods for inference and for model comparison. So with the next version of BayesValidRox, there will be a simplified coupling to the models by using UM-bridge in just more than what I showed to you today, but also allowing for the use of all the other perks that UM-bridge provides. And there will also be more training options, including training with physical constraints or physics-informed surrogates. And thinking more long-term, we plan to make BayesValidRox more customizable and more flexible for the loss with respect to the loss functions, error measures, and also different surrogate structures. And with that, I conclude my talk for you today. I would like to thank you all for your attention And I think I will stop sharing my screen now, so you can ask questions if there's any.